Hi, this is Module 3A, Exponents. So exponents are basically a shorthand for repeated multiplication of a number. In other words, the exponent tells us how many times a number is used as a factor for multiplication. So if we take a look at this example, 3 times 3, that can be written as 3 squared. And so in this next part, this example, the same example, 3 squared, if we look at where the arrows are pointing, the 3 is the base, and the raised number 2 is the exponent, or we can also refer it to as power. And this is basically called exponential notation or form. Okay, so now take a look at 3 to the 5. Again, that means that you have repeated multiplication of 3, but 5 times. Nice, easy concept. So go ahead and do the 2 examples in question 1. And then I also want to take a look at how to evaluate the following. So 3 raised to 3. So I want you to find that button on your calculator, and I'm just going to write down some of the types of buttons you might see on different models. So my sharp one actually has y to the x in order to raise a base to a power, but I've seen some other calculators that have this hat, and other ones that will have the x as the base and y to the exponent. So check out what your calculator has. But if we were to do, let's say A, you should get 27. And let's do question E. So 12 to the 4 in your calculator should give you 20,736. So fill in those other ones in the middle as well, please. Okay, let's look at powers of 10, and I'll just do a few with you. So expanded form is taking exponential form and just literally expanding it. So that's 4 repeated values of 10. So we'll just write that out. And in decimal form, what that's asking you to do is actually evaluate it, just like we did in the previous examples. So that's 4 zeros, 10,000. So if you took 10 and raised it to 4 in your calculator, that's what you would get. I'm going to pick a couple of interesting ones, not the entire chart. So I'm going to look now at 10 to the 0. 10 to the 0, if you were to put this in your calculator, you would get 1. And that's because there is a rule that anything raised to 0 is equal to 1. And I'm going to look at the one below this one, so 10 to the negative 1. So there is this one rule where if you have a negative exponent, you could turn it into a positive if you flip the position of the base. So I just did a lot of stuff there, and I think it'll be more concrete if we put some things down. So in other words, I want you to think about what's underneath this 10 to the 1. Well, there's this invisible 1. If I flip this, meaning I now write 1 over 10, this negative 1 is now a positive 1. So this in expanded form could be written as 1 over 10. And if I evaluate that in my calculator, I get 0.1. I will do one more, because the negatives sometimes tend to be a little bit tricky. So 10 to the negative 2. First thing I'm going to do is I'm going to flip it, 1 over 10 squared. So now that exponent is positive. And if I was expanding that, that really means 1 over 10 times 10. Evaluating that in my calculator, I get 0.01, which is 1/100th, if you want to read that, and that makes sense based on the expanded form. So finish the rest of the chart and check in on your answers with me. Let's now look at something called product property of exponents. So if we think about 10 squared times 10 to the 3, and if I was to expand that, I would get 10 times 10, because that's 10 squared, and then 3 more, because that's 10 cubed. Well, I want you to think about how many 10s you now have in total. You have 10 to the power 5. In other words, how did you get from here to here? Well, when you multiply powers, we add the exponents. And similarly, if we were to look at what's called the quotient property of exponents, and quotient is another word for division, just like product was another word for multiplication. So let's expand 10 to the 5, and I'm going to put this as a fraction because it's going to make a little bit more sense visually, hopefully. So I'll put 10 5s up top, and then a fraction line to indicate my division, and then 2 10s along the bottom. So think about how many of those 10s are canceling between the top and the bottom. So I'll just match them off. There's that first set of 10 and then the second set of 10. So how many 10s are you left with? 10 to the power 3. So once again, how do you get from here to this final answer? When we divide powers, we subtract the exponent, because the 5 minus the 2 is going to get you the 3. So that was a little bit of a basic example on expanding. You certainly wouldn't want to be expanding, you know, when you had like 10 to the 200 divided by 10 to the, 40. You don't want to be writing all those 10s. Just keep that rule in mind. Okay, go ahead and try simplifying some of these. I think what I'll do is maybe a couple of the tricky ones just to get some of the, what I think might be the tricky ones out of the way, and then I'll let you go back and try the others. So let's look at G together. So we talked about the fact that when you have division, you subtract the exponents. So I'm going to have 10 to the negative 2 minus 4. And remember, when you're working with integers, how this proceeds along the number lines. So you're at negative 2 and you go further negative 4 on the number line, so you're at 10 to the negative 6. And let's say an assessment question asked you to give all your answers with positive exponents. Let's practice that concept we just talked about earlier. How do I turn that into a positive exponent? Well, I'm going to flip its position. So 1 over 10, and now that exponent becomes positive. Okay, let's try one more. We'll do H. A little bit similar as to G, but there's just no negative here. So same concept, 10 to the 3 minus 5. That gets us to 10 to the negative 2. 3 minus 5 is negative 2. And I'll do that same thing where I will express my answer with positive exponents. Let's go ahead and do A through F and then check in on your answers. All right, one more concept, roots of perfect squares. So any whole number base with an exponent of 2 is called a perfect square. Let's list some of those perfect squares. 1, 4, 9. I hope you know what I'm listing here. In other words, 1 squared, 2 squared, 3 squared. I'm going to keep going a little bit. 4 squared is 16. Practice some of your mental math, maybe from past math classes. 5 squared, 36, 49, 64, 81, 100, and so on. Don't stress if you don't have this down pat. Not a big deal. You've got your calculator to always double check those things. So our example then, I'll put one down. 5 squared is 25. In other words, 25 is a perfect square. Okay, so the roots of perfect squares are going to give you back whole numbers. So the square root of 25 is 5. The square root of 64 is 8. And you can also do combinations of operations with perfect squares. So let's look at this one. The square root of 64 is 8 minus the square root of 16, which is 4. 8 minus 4 is 4. Go ahead and do question 2. And then also, we already talked a little bit about this, that calculator button. So finish off that you try example, and then please go ahead and try some of this homework. And note what it says. Try the following without a calculator, because you certainly can based on the lesson that we just had.